So now we're ready to look at some more examples where we apply the central limit theorem and find about the probability of certain results when we take samples from a population. We're going to start off here with an example dealing with body temperature again. We have body temperatures of adults being normally distributed with a mean of 98.6 and a standard deviation of 0.73 degrees Fahrenheit. And our question is, what is the probability of a sample of 36 adults having an average normal body temperature that's less than 98.3 degrees? So we have 98.6 here at the middle, and 98.3 is somewhere here on the left. We're not exactly sure how far, but definitely on the left somewhere because it's less than 98.6. The area that we're after, since we're looking for a probability, is the area to the left of 98.3. So that left-hand tail area is what we want. Now, if we wanted to know how extreme this was, how far to the left 98.3 really was, we would plug it into the Z formula, we'd subtract it, and remember we're not just dividing by 0.73 now, but rather a smaller number, 0.73 over the square root of 36. See if you can type this into your calculator right now and calculate this value. And remember, you need parentheses around the bottom quotient and around the top subtraction. But our result is negative 2.47. So we see that a group of 36 people having an average of 98.3, which is only 3/10 off of the normal body temperature, is very rare indeed, negative 2.427 units away from the mean, almost 2.5 units away from normal. And when we look that up, or we put that into normal CDF, we see 0.0068 as the probability that a group of 36 people would have an average body temperature less than 98.3. Very rare. All right, another example, the body temperatures of adults are normally distributed with a mean of 98.6 and a standard deviation of 0.73 degrees Fahrenheit. What's the probability of a sample of 40 adults having an average body temperature greater than 99 degrees Fahrenheit? So here's our setup. Notice that I've replaced X here with X bar, because we're talking about a group of 40 adults. And this time we're above the mean. And notice we're off our mean value by about 0.4, which is 0.4 degrees. And the desired area we're after is above 99 degrees Fahrenheit. All right, it's much easier to use our calculators than finding the Z value that's associated with 99. And that's true for every case. In fact, we don't have to change it into a Z. We can just take that 99 degrees and put it as our lower boundary with something extreme like 1,000, which is sometimes appropriate, mean of 98.6. But notice what we need to put in here for the standard deviation. We need to put in our new standard deviation, and you can actually type it in as a quotient into your calculator. That's usually the best bet to go with, because then you're not rounding off a decimal to too few places, because that'll throw off your answer a little bit. And the result we get is 0.0003 or 3/10,000. Note that we adjusted our standard deviation because we took a sample from the population, not just one single item. Had we just taken a sample of one from the population, our standard deviation would not change. It would be 0.73. But when we're talking about groups of 36, we have to change that standard deviation to fit the distribution of the probability distribution. Let's now contrast the difference. Things change drastically when we change the standard deviation as we have. So we're going to compare. The body temperatures of adults, we're going with the same data set here. But I first want to do, what's the probability that we take a single person from the population and that person, we're trying to figure out what's the probability they have a temperature less than 98.2. So in our probability distribution, if we figure out how far away this one would be from the mean, we see that it's actually not off very far, given my standard deviation of 73 hundredths. We're only at negative 0.547 standard deviations from the mean. That's not even halfway. So 98.2 is not even one standard deviation to the left. It's only half of a standard deviation to the left, a little more. And so the probability of it being less is going to be equal to this entire area to the left of this 98.2. We find that by going normal CDF, negative something large like 1,000, 98.2 upper boundary, mean, comma, standard deviation. We say, okay, there's about a 29% probability, almost a 30% probability, that we take a single person from the population and that their temperature ends up being less than 98.2. Now let's contrast that with the probability of selecting a sample of 36 people and having their temperature, their average temperature of those 36 people, measure less than 98.2. We know that when we take groups of people from the population, that our standard deviation decreases. That means, in essence, and it's kind of logical when you think about it, if I take 36 people from the population, some are going to be on the upper end of the temperature scale, some are going to be on the lower end. But once I start averaging those numbers together, those lower and upper extremities begin to cancel each other out within the averaging process. And so we end up with values that are a lot closer to that middle 98.6 than, say, individuals would be. When I find the z-score for a group of 36, plugging it into the same formula, except we're dividing 0.73 by the square root of 36, we see that we aren't just half a standard deviation to the left, but rather 3.288 standard deviations to the left. That's definitely in the extreme areas of the curve, which in this case would be over here. So that same temperature value is much more less likely when it's a group of 36 people. And we can see how likely it would be to be less than that by finding the probability of that area to the left. And so we replug in the same thing here, except we've changed 0.73 to 0.73 over the square root of 36, giving me 0.0005 as my probability. So here we go. Here's another example for you. I want you to read through this and see if you can write out in probability notation how you would notate this and what the answer is when you calculate it. So pause. All right, so here we're going. A publisher claims that its average book size is 250 pages with a standard deviation of 70. As a reviewer, you get paid per book and not per page to read over the manuscript. What is the probability that you randomly select a book of less than 200 pages to prove? So since we're talking about a single book, we will put the probability of X, original data, one item being less than 200 pages, normal CDF, here we go. There's about, it's almost a 1/4% chance there. Or not a 1/4%, but a 1/4 chance that would happen. Now, what if we had 15 books that we sampled and we took their mean length? What would be the probability that that mean length would be less than 200? See if you can calculate this. Now, I do want to point out one little tidbit that you can use on the TI. Rather than retyping all of this, since we're just changing one part of it, if you hit second entry, or enter, it'll pull up your previous entry, And then all you have to do is toggle over and modify it a little bit, put 70 over the square root of 15. And when you do so, notice how I changed this, not x less than 200, but x bar less than 200. We find that there's a 0.0028% probability that 15 books would have an average mean less than 200 pages. Notice the contrast between these, and that is really the key of the central limit theorem. When we're taking samples from populations, we end up with a totally different curve because the standard deviation changes. And that concludes this portion of this video.